In this video, I am going to explain the point groups of tris-ethylenediamine cobalt-3 ion and tris-glycinato cobalt-3 molecule. Both of these have an octahedral structure. Suppose the metal ion is situated at the origin of a coordinate system. This is the x-axis, this is the y-axis, and this is the z-axis. The metal ion is situated here, and ligands, that is donor atoms, are situated on both sides of the coordinate axis at equal distances from the origin. These are the sides of the donor atoms. If we join these donor atoms by imaginary lines, we will get the structure of an octahedron. It looks like this. And ethylenediamine is NH2, CH2, CH2, NH2. These are the coordinating sites, donor atoms. In case of the tris-ethylenediamine complex, they are bridged, N bridged by this part. Similarly here, N bridged in this manner, N bridged. This is the structure of the tris-ethylenediamine complex. We write En here. And in case of the glycinato complex, glycine is this amino acid anion, NH2CH2, C double bond O, O minus. So for the glycinato complex, we have to replace 3 N atoms by 3 O. That is, we have to write N O here, then N O N O. That will give you the structure of the tris-glycinato complex. Now, in order to reveal the symmetry elements of such octahedral structures, we have to understand first the symmetry of the octahedron. An octahedron looks like this. This is the external shape of an octahedron. There is a square base, and this is a square pyramid on the top. Similarly, another square pyramid below this is fused. There are 6 vertices, 1, 2, 3, 4, 5, 6, and it has 8 triangular faces. And we find that this triangular face has a corresponding oppositely oriented triangular face parallel to it. This face and this face are parallel to one another. The two triangles are kept in a staggered manner. This is shown here separately. This triangle is taken here and this triangle is taken here. Here we can easily understand that it has an axis like this, which is threefold. If we rotate this this octahedron about a line like this by angles of 120 degrees, then this vertex will go here, this will come here, and this will go there. This triangle will not be shifted, only the vertices will exchange their positions. Similarly, these 3 vertices will exchange their positions, but the face will remain there. So this is a threefold rotation axis, C3 axis. There is a C3 axis here. Similarly, taking any pair of opposite faces, you can imagine a C3 axis. There are 4 C3 axes in a pure octahedron. And this figure is more conveniently drawn in this manner. If we take the front triangle in this way and the one opposite to it is staggered with respect to that, the opposite triangle here is drawn in this manner. The front side triangle is above the plane of the paper and the back side triangle is below the plane of the paper. The C3 axis is passing through the center of this triangle and also through the center of the triangle below it. This is the threefold rotation axis perpendicular to the plane of the surface. And we also note that there is a twofold rotation axis. For example, we can rotate this whole triangle about an axis in this manner. We can rotate it about an axis like this. If we rotate to 180, what will happen? This triangle will come to this side and this triangle will go to this side. So there is a twofold rotation axis. Here it is shown in this manner. This is a twofold rotation axis, C2 axis. C3 axis is written in this manner. It is perpendicular to the plane, and the C2 axis is like this. Similarly, there is another C2 axis like this, another like this. There are three C2 axes perpendicular to the C3 axis. And now let us come to the actual cases. We will use this type of diagram for analysis of the actual complex ions or molecules. A star-like diagram. In case of the tris complex, the donor atoms are like this, N, N. Then N, 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 N. This is the structure of the tris ethylene CR whole 3 plus ion. If we use this C3 axis and carry out a threefold rotation, C3 operation, what will happen? Let us label these vertices 1, 2, 3, 4, 5, 6. All are nitrogen atoms. We can execute a C3 operation. What will happen? 1 will come here, 2 will go here, but this upper triangle will remain on the upper side of the octahedron, and the lower triangle indicated by red line will remain below the plane of the paper. But only the vertices will change their positions. By anticlockwise rotation, 1 will come here, 3 will go here, and 2 goes here. And similarly, 4 by anticlockwise rotation comes here, 6 goes there, and 5 goes to this place. Now here we find that 1 and 5 are bridged. So here we have to bridge 1 and 5. Similarly, here we see that 2 and 6 are bridged. So we have to bridge 2 and 6. 2 and 6. Similarly, here 3 and 4 are bridged. So 3 and 4 are to be connected. Now we now see that this configuration, if we call it 2 and this configuration 1, then we see that these two configurations are equivalent. 2 is equivalent to 1. Therefore, C3 axis exists, C3 exists. Now, let us try to find a twofold axis. If we use this line as a twofold rotation axis and carry out the C2 operation, what will happen? 180 rotation. By 180 rotation about this line, what will happen? The lower triangle drawn by red ink will come to the upper side, and the upper triangle drawn in blue ink will be transferred to the lower side. So this will now look like this, and 3 and 5 will exchange places because the rotation axis is this. 3 and 5 will exchange places. 3 will come here. No, this is 1. 1 and 5 will exchange places. This will come here 1 and this will be 5. Similarly, 4 and 2, they will exchange places. 4 will come here and 2 goes there. 3 and 6 exchange places. 3 comes here and 6 goes here. And here we find 1 and 5 to be bridged. So here we have to bridge 1 and 5. Similarly, here we see 2 and 6 to be bridged. That is, this is the ethylenediamine moiety, 2, 6. So 2 and 6 are to be connected. By that rotation, this part goes to this position. And similarly, 4 and 3 are bridged. 4 and 3 are to be bridged. We see that the configuration 1 and this new configuration 3, they are the same. 1 and 3 are equivalent, not the same, they are equivalent. 3 is also equivalent to 1. 1 is like this and 3 is like this. So this C2 axis exists. C2 exists. And how many C2 axes are possible? One is like this, another will be like this, and another will be like this. All three will be perpendicular to the principal C3 axis. So we have C3 and 3 C2 axes perpendicular to C3. Therefore, the structure point group is of D3 type. Now, let us try to find whether any symmetry plane exists or not. If we imagine a horizontal symmetry plane means a plane between these two triangles and perpendicular to the principal axis. If we imagine a plane between the two, one is above the plane and another is below the plane. If we imagine a symmetry plane in that region between the two triangles, then that plane will not act as a mirror plane because the upper triangle is not the mirror image of the lower one. They are in a staggered orientation. Therefore, sigma h does not exist. There is no sigma h. Then we may try to find whether any vertical plane like this exists. We see that the two sides of this plane are not the same. This side has a bridge, the other side does not have. So such a plane also does not exist. A vertical plane containing the principal axis does not exist. Between these two C2 axes, we can imagine a symmetry plane in this manner. Here also we see that the two sides are not similar. The two sides are not similar. If this is the plane, then this has to have an image in this position, but this position has no bridge. So this has no image on this side. Similarly, this has no image on this side, and so on. So the dihedral planes, this may be another dihedral plane between two C2 axes. Between two C2 axes, this is one. Similarly, between these two, this is two, another. But none of them can act as a true symmetry plane. So, sigma V or sigma D do not exist. Sigma H also do not exist. Therefore, what should be the point group in this case? It will be only D3. The point group of this tris complex molecule is D3. If instead of ethylenediamine we take tris oxalato complex, oxalate ion is like this: C double bond O, O minus, C double bond O, O minus. We can take this instead of ethylenediamine. Then also the tris complex will be like ethylenediamine. That also will belong to point group D3. And let us next consider the tris glycinato complex. In that case, we have N, O, N, O, N, O. Like this, the glycinato complex. Here we see that the C3 axis exists because this triangle has three similar atoms. Similarly, the lower triangle also has three similar atoms. So we can rotate this whole through one angle of 120 degree about this axis, perpendicular axis. So C3 exists, C3 axis exists, but C2 does not exist. C2, if we imagine a C2, then the two sides are not the same. So C2 axis does not exist. Only C3 exists, and of course the identity exists, and no symmetry plane, either horizontal or dihedral. And therefore in this case the point group is C3. Tris glycinato cobalt 3 molecule has a point group C3. All these molecules that we have discussed today are optically active. They are chiral, optically active, because the condition of chirality is no eye, no inversion center, no reflection plane of symmetry, and no SN axis. This is the criterion for chirality. Only CN and DN type of groups, can satisfy this condition. So this object, that is the tris glycinato complex and the tris oxalato or tris ethylenediamine complex are all optically active. With this, I complete my discussion today. I thank you very much for watching the video.